general relativity step by step. I've been looking at the linearized Einstein field equations, hoping to find gravitational waves, and we've found a solution in this form here, which satisfies the linearized Einstein field equations. But it's still pretty complicated. We've got a few relationships that we dug up from the Lorentz condition and from the Einstein field equations, but we've still got this rather complicated object here, this second-rank tensor. And in this screencast and the next 3 or 4, I'm going to try and simplify that A matrix or that A tensor to a form that we can work with and visualize more easily. So how do we do that? Well, the first thing I wanted to do was to remind you what the gauge transformations were. We wanted, I'm not sure why it does that, we wanted to insist that di mu h bar mu nu was equal to 0. And we did this by using a gauge transformation. X alpha maps under a gauge transformation to X alpha plus a small perturbation of X0 through X3. And what did that do? That mapped di mu h, oh no, it's an h bar mu nu, maps to, under the gauge transformation of psi, I suppose. It went to what it was before, but minus di mu psi nu. And I showed how we could always find a psi that that satisfied that we could find psi with di mu upstairs psi nu equals di mu h bar mu nu, and because the sign was opposite, we would be satisfying the Lorentz gauge condition here. Spent a long time talking about this. What I'm going to do now is I want to observe that we can simplify the. We haven't exhausted our freedom. We haven't exhausted the Lorentz gauge freedom yet. What I want to do is I'm going to make another gauge transformation of theta, let's say. And what does that do? That sends us to what we were before, minus the effect of the di mu psi nu. But now we've got another subsequent transformation, another subsequent gauge transformation, which is going to do this. Theta, let's say, nu. So what I want to do is we've just applied the regular one, which we used to impose the gauge condition, and then I'm going to try and find another theta which does this. And then people are going to say, well, no, that's crazy, because you've gone to all this effort. You've gone to all this effort to satisfy the Lorentz gauge condition. We now have a nice Lorentz gauge condition equals 0, and you've stuffed it up by choosing this extra theta here. And I say, but if I can find, if theta has the property that di mu theta nu equals 0, no harm is done. Because we're subtracting from the trace, from the Lorentz condition, we'll be subtracting 0 if I can find a theta. Now what I'd like to do is to give you a general class of transforms, a general sort of characterization of what theta is, but that's too hard. So what I'm going to do is I'm going to find an example theta with the required property di mu theta nu equals 0, and I'm going to use that, and I'm going to use that version of theta. And you spend a little bit of time thinking about it, and eventually you realize that the best transformation, or the nicest way to write it, is theta, let me get my notation right, mu equals some vector b, which I'll come back to, times sine of k alpha x alpha. And then what I'm going to do, how long has this one been going? That's been going for 4 minutes. Yeah, this doesn't make any sense unless you can demonstrate that theta has got the right properties. So see, I'm mixing my, that should have been a new, not a mu. New, and that should have been a new. There it is. New. So what I want to do is to find di mu of theta nu, and it had better be equal to 0 because I don't want to stuff up my Lorentz gauge. I want to subtract nothing from my Lorentz gauge. So in a way, this theta transformation, this second gauge transformation indexed by theta, isn't doing any good. Well, it is doing some good, and we'll see what good we can do with it, but it's like doing the Rubik's Cube. I'm trying to do the top layer of this Rubik's Cube without stuffing up the bottom layers. So I don't want to undo the good work I've already done. So that places a very severe restriction on what theta can be, but this will satisfy our requirements, and I'll show that now. Let me write that equation down. We've got G alpha beta di alpha di beta acting on theta nu. And because we're working to first order, that means I can replace it with the flat space metrics 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, alpha beta di beta theta nu equals. I'm going to go up here. Eta alpha beta di beta b, what was it? Nu sine k alpha x alpha, sine k alpha x alpha. Wonderful stuff. I'm going to observe that this is constant. I can do that in a different colour. Very mindful of I've had quite a few emails from people telling me they don't like just black and white. They want it to be a bit more brightly coloured. Well, I'm happy to oblige. There we go. Blue, that goes to the front. There we go. Blue. This interface is going to drive me insane. Blonde. Okay, so it's eta alpha beta di alpha. No, I was going to move the b, wasn't I? B nu di alpha di beta of sine k alpha x alpha, and we'll apply the same trick that we did last time. So it's eta alpha beta b nu di alpha of di beta, that's going to be k beta, differentiate sine, it goes to cos k alpha x alpha, brackets to close there. Now do this differential here, eta alpha beta beta nu. Oops, don't like it when it does that. Just a minute, I'll have to kill that. And now we've got a minus k alpha k beta sine, it's differentiated cos, it turns to a sine, k alpha x alpha. That sign goes there, I guess. Equals b nu, oh there's a minus there, sine k alpha x alpha, that term's there. We've got an, I'm going to use one of those indices to raise it. That's going to be a k beta. Do you see what I've done? I've used this index here. I'm going to use a nice colour for this. Just a minute. Green. I'm going to use that beta there to raise. Oh no, not that beta. I'm going to use that. I'm going to raise that beta. I'm going to use that alpha there. Oh, for goodness sake. I'm going to raise that alpha there with this one here. Turn it into a beta. And I'm going to put brackets around there. And then I'm going to observe that this equals 0. Why? Because k, by construction, is a null vector, and that came from the linearized field equations. Fantastic. Fantastic. Let me just summarize all of that again. We had a gauge transformation of psi, which we used to satisfy the Lorentz gauge, which is this equation here. And then I wanted to have another gauge transformation that didn't stuff up the Lorentz gauge. But I was wondering, if there's extra freedom I've got, can I find a theta which doesn't stuff up my Lorentz gauge? And yes, we can. because here I found it. Yes, I pulled it out of thin air, but what happens when you do research into this is that you try 3 or 4 simple examples. You try a constant, you try a zero, you try linear, you try this, and then you try this guy here. And then we did all this stuff here, and we showed that indeed that equation there held. So what that means is that theta, which is here, doesn't stuff up my Lorentz gauge. So I can use, I'll write it down, I can use theta, and this does not stuff up the Lorentz gauge condition. Why? Because what it does, it subtracts di mu, theta nu, theta nu, which was equal to 0. Nu. Yeah, sorry, my interface is misbehaving again. Where was I? We can use a subsequent gauge transformation, so long as it satisfies this, that's no problem. And I showed that that condition was in fact met for this class of transformations here, which I'm going to use of my further gauge freedom, my further coordinate freedom, to further simplify my linear solutions to the field equations which are here. Stop.